Hi everyone, welcome back to our lesson this week on rules of probability. I hope you're doing well and that remote learning or digital learning is starting to fall into place and you're getting a routine down. So what we're going to look at in this session is some of the rules and some of the more fine-tuning details of probability. So let's get into it. So our plan for this is to just cover different rules of probability, and we'll start to connect these in the coming weeks. Just they all overlap ultimately, but there's a few more visual ways of displaying and just ways of finding values before we really get into combining all of these together. So starting out, we're going to just real quick cover sample space again. This was back in the video probably 2 or 3 weeks ago. I can't recall which week it was exactly. So we want to show the sample space for flipping a coin and rolling a die. So I'm going to do this via the grid rather than a tree diagram because it's going to be really messy. And I'm not going to try and write out, well, I can get a 1 in a heads, I can get a 1 in a tails. I'm going to create a systematic grid to show that. So if I show the outcomes of my coin, and I actually want to move that to make it I want to make the rows the coin and the columns the dice. So here's my die, and there's my coin. So what I'm going to do here is show the outcomes of the die. So with the die, I can have a 1, 2, 3, 4, 5, or 6. And then with the coin, I can have a heads or a tails. And as I build this, I can create a grid that shows all of the outcomes, and I'll list all of those. So this would be the sample space. It could be everything that can occur if I do these two options, run some trials. So if we go ahead and write this out, I can have, if I flip the coin first, I can have a heads and a 1 or a tails and a 1. I can have a heads and a 2 or a tails and a 2. I can have a heads and a 3 or a tails and a 3, and all the way down. And then finally heads and a 6 or a tails and a 6. So if I were to ask, well, what's the probability that I get a heads and roll a 3, I just look at this and I say, well, there's only one of these outcomes in the sample space that satisfy it, and there's 6, there's 12 total. So that would be my probability. Now where I'm getting at here is, say I wanted to roll 4 dice and 3 coins, and I want the probability of a heads and a 3. It starts to get more complex. Or if I want to roll a 50-sided dice and a coin and flip a coin at the same time. This takes a lot of time. It starts to get tedious. So there's a way to figure this out, and that's what we're going to get to, is how do we calculate that without having to draw this entire sample space diagram every time and see that, well, one of my 12 outcomes satisfy that requirement. And the way we do that is with what's called independent events. So what we just went over, flipping a coin and rolling a die, are independent events. And what I mean by independent events are when I think about the outcome of one, whatever happens there. So say I flip a coin and I get a heads, I roll a dice and I get a 3. The fact that I rolled a heads with the dice, with the coin, the fact that I flipped the coin and had a heads and rolled the dice and had a 3 have no impact on one another. They're independent of one another. So why that matters is when I have independent events, I know that the outcome of one does not impact the outcome of the other. I can say that the probability of these outcomes happening, so the probability of a heads and a 3 is equivalent to the probability of a heads happening multiplied by the probability of a 3. So I can multiply these two probabilities, and I don't know why I just put A there. That should be probability of heads. Normally we say A and B if two events are independent. So this, oh geez, where am I going here? This would be probability of heads. And we can see that, well, I know the probability of heads is a 1 in 2 chance. I know the probability of 3 is a 1 in 6 chance. And multiplying 1 by 1, 2 by 6, I get 1 in 12. This process is a lot more streamlined than going back and writing out this and seeing, well, one of the 12 outcomes. What this tells me is one of the 12 outcomes satisfy this requirement. So when two events are independent, we say the probability of A and B, if we want to generalize this. So the probability of event A happening and B, whenever we say and, we multiply, is the probability of A times the probability of B. These would be independent events. So events that are independent are pretty straightforward. They're clearly the outcome of one doesn't impact the outcome of the other. So it could be something like if I draw a marble from a bag and I flip a coin. Those two are not going to impact one another. It could be like the probability that I wear shoes and a t-shirt, just a bunch of different events that don't impact one another. Events that are not independent would be like where one event impacts the other. So like if I draw a card, then I draw another card from a deck without replacing it. So when it starts to impact the other, we have a way of dealing with that, and we'll look at it next week actually with a tree diagram. So let's go over a couple example problems, and then we'll get into the second topic here. I'm going to try and keep this pretty short. So we roll a fair die. I just put that there because it's not weighted. It's thrown twice. So what's the probability of getting 2 3s? So if I want the probability of 2 3s, the fact that I roll a 3 the first time doesn't impact the fact that I roll a 3 the second time. They're independent events. So to do this, I do the probability of rolling a 3 and rolling a 3 again would be equal to the probability of 3 times the probability of 3. Well, if I roll a die, there's a 1 in 6 chance to roll a 3, a 1 in 6 chance to roll a 3 again. So this would be a 1 in 36 chance of doing it twice in a row. And there we have it. We're done. We could write this as 1 over 36 reduces to, or we can say 0.0278 would be the probability of that happening. I should say 6-sided die here, but we just assumed that. All right, on to the next one. If I flip 3 coins simultaneously, what's the probability that all 3 land on heads? So if we were to do this with a sample space diagram, I would have to start writing out, well, I want heads, heads, heads. I can have heads, heads, tails. So like this is the outcome I want. And then I could also have heads, heads, tails. I could also have heads, tails, tails. This starts to get messy. So we recognize these are independent events. The fact that one coin being heads doesn't impact the other one being heads at all. So this would be the probability of HHH. So it would be a 1 in 2 chance for the first, 1 in 2 chance for the second, 1 in 2 chance for the third, and this would be 1 in 8 of the outcomes would be all heads. So we can leave it as 1/8, or we can write this as 0.125 is the probability as well. You can see this speeds up the process quite a bit. We just have to recognize they're independent events. And typically, events that are not independent have some sort of non-replacement, so drawing a deck from a deck of cards or something like that. All right, last question. 2 die are thrown, a red one and a green one, simultaneously. What's the probability of the red die being even and the green die being a 6? So what we want here is the probability of even on the first die and a 6 on the second die. These are independent events. The fact that I roll a even does not impact the fact that I roll a 6 on the other die. So the first die being even, if it's 6-sided, would be a 1 in 2 chance, and then the probability of a 6 is a 1 in 6 chance. So here we would have a 1 in 12, or whatever that 1 in 12 chance, which would be, or 0.0833. So there we have it. Speeds up the process quite a bit. So that's one thing we're going to talk about, our independent events. The second of the 3 is called the addition rule. Now this kind of drifts off from it, but it still deals with the intersection and union and that notation. So the addition rule is something that we've actually already done, but we didn't know we were doing it, unless you've done statistics or some probability is what this is. You didn't know we were using the addition rule. So I'm going to write this out real quick. So the addition rule says that the probability of A union B, of A or B occurring, is equal to the probability of A plus the probability of B minus the probability of A intersect B, or A and B. Before you continue this, I'd encourage you to pause real quick and think about why this makes sense. Okay, so let's get into this. So what's nice about this, and why we spent some time on Venn diagrams, is showing this is a lot easier than explaining it. So if we draw out a Venn diagram with A and B as our 2 events that can occur, I have some set here that's A. I have another set here that's B. Oh my gosh, that circle is going to drive me crazy. I have some set here, that's A. I have some set here, not any better, that's B, but we'll go with it. And I want the probability of A union B. So this is where the shading ties in. If I shade A union B, I shade all of set A as well as all of set B and what they share. Oh my, that just got really small. All right. So I shade this, all of set A, and I shade all of set B. So if you look at that, what I shaded twice, and I did that intentionally, is the overlap. So if I want the probability of A union B, well, what I can do there, and it makes total sense looking at this equation, it doesn't come out of thin air. I take A, the probability of A happening, which is right here, and I add the probability of B happening. But what you notice there is that I just shaded one region, or I included one region twice. I double counted the overlap here, so I need to take one of those overlaps away. So A intersect B needs to go out of that one time, because I counted it 1 2 times when I added A and B together. So to get the union, A union B, I add A, I add B, and I take away one of the overlaps. This generalizes really nicely, actually, because now we can just build an equation from it. Second thing in this topic are events that are mutually exclusive. These are events that share nothing. They have nothing in common. So mutually exclusive events on a Venn diagram would look like this. Here's A, here's B. And why I bring this up is you notice there's no overlap here. So if I have two events that are mutually exclusive, the rule tells me how to test for it also that I'm about to write. If I have mutually exclusive events, I know the probability of A union B happening is just the probability of A plus the probability of B. I don't need to subtract the overlap here because I don't have an overlap. They don't share anything in common. There's no intersection. So it would be plus 0 there. So what this tells us is if our Venn diagrams look like this, I could have a class, say, let's make up an example, where I'm looking at the number of students in French and the number of students in Spanish in like a math class. Well, typically those would be mutually exclusive. There wouldn't be an overlap. So if I wanted the number of students in French or Spanish, I would just add French to Spanish and not worry about the ones that are in both because that doesn't happen very much. So I can test and see if they're mutually exclusive as well. If this is true, the events are mutually exclusive. So if the numbers match here, it's mutually exclusive, or if I have this situation where the Venn diagrams look like this, it's mutually exclusive as well. So let's get into a practice problem here, then we'll call it good. So we want to find the probability of A intersect B here. So we know the probability of A is 0.5, the probability of B is 0.6, probability of A or B is 0.9, and I want to find the intersection. You could very well draw a Venn diagram and go through and do this, but now we have a rule actually that kind of abstracts away from the Venn diagram. It does it a little more efficiently for us, and that's what we're interested in right now. So I know that the probability by the addition rule of A union B is equal to the probability of A plus the probability of B minus the overlap because that's part of A and B. So probability of A and B, we subtract one of them. So if I want to solve this, I just plug the numbers in and we're tying this into algebra now. So A union B is 0.9, A is 0.5, B is 0.6, and then we subtract the overlap because we don't want to double count that. But in this case, that's actually what we're solving for. So if you were curious earlier why there were negative values going, or why it was bigger than 1, this happens and that's bigger than 1 as well. So 0.9 is equal to 1.1 in the example problems I was talking about. Why sometimes you added the numbers and it was bigger than the total in the class? Well, you were double counting the overlap. You weren't taking away that overlap. So 1.1 minus the probability of A and B occurring. So now we just solved this. Take 1.1 away, minus 1.1 to get this 0. So I have a negative probability of A intersect, probability of A, I forgot the A there. Probability of A intersect B is negative 0.2. So that's okay that this is negative 0.2 because this is the negative probability of A and B. So we just multiply by negative 1 or we flip the signs. So 0.2 is probability of A and B. So this week basically is more on a more efficient way of doing this. So we had a more efficient way of doing this than a Venn diagram. We didn't even have to think about what it was. We just used the rule of probability. So look for a couple practice problems, and then the assignment on Wednesday is a little different as well if you haven't looked at that yet. I hope this video helped. We'll see you soon.